Quantitative Data Analysis Techniques, Assignment 4.5.1 by James Boxford. Right. Data preparation. So, a researcher may have to collect a large amount of quantitative data, and then the data that they've collected needs to be structured and organised. This is so that it can help them identify any anomalies in the data and anything that any patterns or anything that they think probably shouldn't be there. So there are different things that the researcher needs to find before they can continue, and these are the range, the rank order distribution, the simple frequency distribution, and the group frequency distribution. I'll explain these in a moment. So the range. The range is defined as the distance in numerical value from the highest to the lowest collected value. To calculate the range, you subtract the lowest value from the highest value. In the next slide, I have used data from the standing vertical jump to explain the range and show you an example. There are many positives and negatives about the range. The range is very good because it can give you the value from the highest to the lowest, and it doesn't matter about the values in between. However, the issue with the range is that you could have a value that's 12, and you can have a value that's 112, sorry. Your range would then be 100. If all your other values other than 12 are 13, 14, 15 through maybe 20, that isn't a true reflection on this one other value. So there are some issues with the range. Here's the example for the range. So here the range would be the lowest number minus the highest number. So in this example, the lowest value is 15, as you can see highlighted red here, and then that's the lowest value, and then the highest value is 56 here. So the range would be 56 minus 15, which gives you a score of 41. And the range for the standing vertical jump is 41. And as you can see, there are other values that are around that number anyway. So you could say that this is a true reflection of the actual range. If this 56 number was 75, the range would be a lot higher. The range would then be 60, and there are no values that are at that range, at that level. So the range is accurate in this example. Rank order distribution. So rank order distribution is where the data is placed into a list and the values are organised from highest to lowest. This data is organised in a singular column, and this should only be used whenever you have 20 or less values. This is because if you're ordering numbers from maybe 1 to 150, it's going to take a considerably long time, even if you have Excel, and your table would be dramatically too big. But the rank order distribution is very helpful with other things as well. So for the range that I explained on the last slide, having the data rank ordered can help you identify that's the lowest value, that's the highest value, and you won't have to worry about going through the data if you've got 20 odd sets of data saying, okay, that's 5, that's 10, and so forth. So here I have some rank order distribution data. So on the left, I've gone for the height of participants in a basketball team. So the red table is where the data is not ordered. As you can see, you've got values of 175.5 centimeters all the way down to the bottom of 164 centimeters. If you were trying to work out things like the range for this, it would take you a while because you'd have to go, the first one's higher than the second one one's higher than the third one's higher than the second one, and so forth. However, on the right hand side of my slide, the green table, I have rank ordered this data. This data is a lot clearer and easier to be interpreted as well, because anybody can just go down and say the first value is the lowest, and so forth. Simple frequency distribution. So this involves using one column where all of the raw data is stored, and then having a second column where the frequency values are. The frequency column contains the number of times that a specific score was achieved. This can be used when the number of values is greater than 20 or when the range is above or equal to 20 as well. So the raw data for the skin fold caliper test on the biceps, as you can see, is in this table here. So this data has not been rank ordered, it hasn't been touched at all, it's just been inserted straight in. And then what you then do is break down the data here. So here in the simple frequency distribution table, along with the cumulative frequency, which I'll explain in a moment, is where you see the frequency and all the others. So I've identified the numbers. So 4 comes up, 5 comes up, 6 comes up, 8 comes up, 10, 15, 16, 19. And then I go on to how many times this data has come up. So the value of 4 centimeters has come up 3 times. So I'd tally this down as 3, and then I'd say it has a frequency of 3. 5 occurred 4 times, frequency of 4. 6, 1, frequency of 1, and so forth. The cumulative frequency is a way of seeing the values of how many numbers you have, So what you do is you start on the first, you look at your frequency. The first frequency is 3, so the cumulative frequency will be 3 for this. The next frequency is 4. You then add this to the 3 you gathered in the first from the first value, and so forth. Then you got to add 1 for 8, 1 for 9, 2 because the value for the 10 centimeters was 2. That brings the frequency to 11, all the way to 14. That number at the bottom there should match the amount of data that you have in your raw data table. Grouped frequency distribution. So group frequency distribution involves grouping 2 different sets of data together that are in the same results. This works when the number of values is less than 20 and when the range is less than 21. The group intervals are calculated by range and then divided by 15. So here is the raw data for the width of a bicep measured. I've used the same data as on the previous slide. And here is the group frequency distribution table to the right. So what you can see is I've identified it in groups of 5. So I've got 0 to 5, 6 to 10, 11 to 15, 16 to 20, and then 21 plus. I went 21 plus because there was only one value over 20, and there was no need to go for 21 to 26. No, 21 to 25, sorry. So, as I've identified, the grouping of 0 to 5 occurs 5 times. The grouping of 6 to 10 occurs 4, 11 to 15, 2, 16 to 20 twice, and 21 plus is 1. This is a good way of seeing frequency and also what grouping the frequency is in. However, it is not as expansive as the cumulative frequency tables because you can't see specifically for what value it occurred. So the part 2, presenting data tables. So tables are a very good way of presenting data because it can show you exactly what occurred where. So if you look at the first table, the orange table up here, this is my raw data table. As you can see, none of the data is rank ordered, and it all becomes very jumbled. You have the highest values at the top and the lowest values at the bottom in some cases. The data is very hard to interpret for people that won't understand what is going on. However, the one good thing is that all the participants' scores are level for each one. So participant A in the sit and reach scored 25, in the vertical jump scored 16, and their peak flow was 640. This is all ordered. This is the only ordering that there is on the table. The second table is my rank order table. So in this, I have had to move around the participants because the score for the sit and reach, the lowest sit and reach score was 22. However, if you look at participant M for the sit and reach, their score was 22, which was the lowest. However, their score for the peak flow was 500. This is not the lowest score. So you have to move around the table, but it is still able to be interpreted as there is a column for the participants on each side. So you can see if you were looking for participant D every time, you'd identify that they were there, and then moved there, and then there to the end. So it's a way of making the data more presentable, but also easier to be interpreted. And the final table I've got here is another way of ordering it. So the data is still rank ordered. However, I've ordered it by its mean, its standard distribution, and its range. This is just another way of ordering it, and it can become clearer it will become clearer later on why the standard distribution, the mean, and the range are such a good way of ordering data. Scatter graphs. Scatter graphs are a good way of presenting data, and this is because you can identify where all the points were for certain things, and then you can also add a line of best fit to them all, or where the data should possibly lie. From this, you can get an idea of whether there is a strong positive correlation, a strong negative correlation, a weak positive, a weak negative, or if there's no correlation at all. For my data here, I would say that there is no correlation. And this is because all the data is spread out, and there isn't much of a way to suggest which way it's traveling. I could say it's positive, but due to the widespread of data, so the results of 13 up here and 12, 12, and 11, you can't tell whether it's meant to be a positive or a negative. So the best way for this is no correlation. And in some cases, many graphs are very tight and packed together. And in this case, you could say that it is a strong positive or a strong negative. The issues with scatter graphs are that you need a certain amount of data, because if you have very high numbers or very low numbers, the data can become very clustered. And if you aren't using the right axes, then it won't work either. So if I had, also my lowest point here is, the value is 3. However, if I had a data that was 33, this table would be very long, and this value down here would be a lot smaller than it should be because of the spread of data. So that's one thing you need to consider when using a scatter graph. Line graph. So line graphs are a way of identifying two different pieces of data as well, and using a legend at the bottom when using two pieces of data can make it a lot clearer. So the reason for using a line graph is if you have large numerical values, or just numerical values that link up and you want to show them in their ascent and descent. So something good to use for a line graph is something like heart rate over the course of exercise. So you could have heart rate up here and time along there. This was not in the data set that I had. So I decided to use bicep and tricep skin fold measures. This is because you can see, as it varies through the participant, you can see what values they scored. The bars here are the standard deviation bars. So this is saying the value should lie between this point and this point. However, as you can see here, we have some anomalies. So participant 10 scored 19. The standard deviation predicted them to only have been able to score a max 13 or 11. So there are some issues with line graphs, but yeah. Bar chart. Bar charts are a good graph to use to show correlation. So here I've used thigh girth and standing vertical jump. You can see for participant A that their thigh girth was 41 and they scored a standing vertical jump of 16. And you can also see that as the thigh girth increases, standing vertical jump scores also increase. However, over here, the smaller thigh girth has produced a large jump. So there is a way of showing the correlation with a bar graph. However, bar graphs can have some inaccuracies if they are made incorrectly. So, for example, if a bar graph is used in the wrong sense, so someone uses a 3D bar graph rather than a 2D one like I've used here, or they decide to use data that shouldn't actually fit in the bar graph, so use data that's really large or really thin, it can impact it as well. This is the end of part 1.